Hello, welcome to another lesson from Proflan YouTube channel. In this particular video, we're going to talk about parametric differentiation. Remember, an equation or equation of a curve can be given in terms of parametric equation. Now, first we're going to look at what do we mean by parametric equations. Remember, parametric equations, these are equations where the variables given x and y are given in terms of the third variable t. So for an example, we can be having this kind of equation. X is expressed as x equals to 5 cos t, and y is also given as 1 minus x squared t. So which means we have two equations, x and y, which are expressed in terms of the third variable t. Another example in this regard can also be given as x equals to 5 cos, that is 1 plus 4 sin t, and also we have y equals to 2 cos t. Now t is the third and t is going to be the parameter. So if you are told to identify the parameter, this t in these two equations is the parameter, and we can now go ahead and say the given equations x, y, these are the parametric equation. So next we're going to see that these parametric equations can be differentiated so that we can be able to get dy dx, and we're going to see that prominently the rule that we're going to use in order to differentiate these is chain rule. And if you have not mastered how to differentiate using chain rule, you can check in the description. There are more videos on the same content. Now we need to move further down so that we can be able to see how do you differentiate parametrically. So we are going to identify and say that in order to differentiate, let's just go into it. dy dx is going to be obtained by chain rule, and is going to be dy dt, then we shall divide by, in order to have dy, when you differentiate x with respect to t, take note of that. When you differentiate x with respect to t, we are going to obtain dx dt. In the second part, when you differentiate the y function, the equation y with respect to t, you are going to obtain dy dt. So how are you going to get dy dx? We're going to say, in order to get dy dx, it's going to be this part, dy dt divide by dy dt divide by dx dt. But you see, if you're having a division and you have a fraction, you are going to find the inverse of the second fraction, and this is going to be given as dy dx equals to dy dt times dt dx. But you can see now in this new equation, dy dt times dt dx, you can cancel dt, and then you're gonna remain with what? Dy dx. Now let us go and dive in so that we can be able to look at different examples, and you get to understand deeper and have a deeper connection in this concept of parametric differentiation. So the first example, we're given parametric equations here. Let's go into it. We are told that given a curve is represented, let's write that. Given a curve is represented by parametric equations, x equals to 3t and y equals to t cubed plus 4t squared minus 3t. Now, in order to get dy dt to this, we are going to differentiate the first, the equation y equals to 3t, 3 power t plus 4t squared minus 3t. Which means that we are going to lower the power. We are going to take the power down so and reduce the power by 1. I believe that's basic differentiation that you can be able to do. So let us go on. This is going to be 3t squared plus 8t minus 3. dx dt, if we differentiate 3t, we are going to get 3. Now, in order to get dy dx, it will be dy dt divided by dx dt. So that we can substitute, already we have gotten those differential functions for the dy dt and dx dt, so that we can be able to say dy dx is going to be that divided by 3. And now this is a point where we were supposed to find dy dx. Now in part B, we are supposed to find values of t in these functions where the gradient is equal to 0, where dy dt is equal to 0. So let us just put this down properly so that you can be able to move to the next part. We are finding values of t for which the gradient is 0. So it means if gradient is 0, it means this part also is going to be 0. Then we're going to say now 3t squared plus 8t minus 3 over t should be equal to 0. Multiply 3 both sides. We are going to remain with this equation, which we can factorize and then solve. So t is going to be 1 over 3 and t equals to negative 3. So that's the end of the first example. Let's move further, where you are given trigonometric functions. How are you going to work it out? We are supposed to find dy dt. Let's see the question and the information it entails. So we are given x equals to 2 sine theta and y equals to 1 minus 3 equals 2 theta. We're supposed to find the exact gradient at theta equals to pi over 3. So what you need to realize now, our parameter is theta in this case, and we have two parametric equations of x and y. So first thing first, we are going to start by finding dy d theta. We are finding dy d theta. So we can be able to write this down. Dy d theta is going to be, now you see we are having 1 minus 3 cos 2 theta. Remember, 1 is a constant. So if you differentiate a constant, you are going to get 0. So we are not going to consider that. We shall leave it out. The part that we shall focus on differentiating is negative 3 cos 2 theta. So that is going to reduce to 3, of course, is a constant. You just leave it there. And at that point, we are going to use chain rule. So first, we are going to write the negative 3 there. That's negative 3. Now, if you differentiate cos 2 theta, don't look at the 2 theta. Just look at this is a cosine. If you differentiate a cosine, you are going to get a negative sine of 2 theta. Now, once you have gotten that, now you go into the inner part of the function, which is 2 theta. If you differentiate 2 theta, you are going to get the answer 2. So meaning our final part, because we're having negative 3 there, we are going to have it on this function. So negative 3 is there, so that will be negative. And the final part of this is going to be positive 6 sine 2 theta as dy d theta. Now moving to the second equation, dx d theta is going to be actually 2 cos theta, because if you differentiate sine theta, you get cos theta. Then now, in order to get dy dx, we are going to say is dy d theta over dx d theta. Then since we have the expression for the same, we are going to say that is 6 sine 2 theta over 2 cos theta. But you need to remember, we can cancel this, but you remember from double angle identities, and that is from trigonometry, we can be able to have this much simplified, because we had learned that sine 2 theta can be expressed in that particular manner. So that information is very important in order to simplify this. So which means sine 2 theta can be replaced, those are replaced with 2 sine theta cos theta. So this dy dx can be further given as that and of course we are going to cancel cosine and cosine, and then we shall remain with 6 sine theta. Now since we were told we are finding the exact gradient at that particular point, and 6 sine theta is the gradient function, we're going to substitute theta, which is pi over 3, into dy dx, and basically this is going to be what? We are finding dy dx at the point where theta is pi over 3. We shall substitute into this, and then we are going to have our answer as a 6 times root 3 over 2. So if we cancel 6 and 2, we are going to get 3 root 3 as the exact gradient to this particular question. So we need to move down to another example that maybe you can be given, and this can enable you understand further. We are supposed to work out where we're given these parametric equations, and then we're supposed to find the equation of the normal to the curve at the point t equals to 0. So the starting point here is first to differentiate this parametric equation. So dy dt is going to be the first term. If you differentiate it, you get 0. Now the second term of the equation of y, remember the way you differentiate exponents. So we are going to use product rule at this point, because we are having 2t and exponent t. So we shall keep exponent t constant and differentiate 2t, which is going to be 2, plus we shall keep now 2t constant. We differentiate the exponent t, we are going to get the exponent part. So which means our final answer becomes 2 exponent t plus 2t exponent t. Right? Now we move next to dx dt, of which we're going to get, in order to actually differentiate exponent of 2t, remember you are going to differentiate the power and then multiply it to the exponent, the original exponent that you are having. So if you differentiate 2t, you are going to get 2, then you multiply that to exponent 2t. So dy dx is going to be the division of that, and then if we substitute and simplify these guys, we're going to remain with this part cancelling out, and then we shall have now a final expression as 1 plus t over exponent of t. But you need to remember, this is the differential function. Then it will mean that we need to substitute t equals to 0 in order to get the gradient, and the gradient is going to be 1. A normal and a tangent, a normal and a curve meet at 90 degrees. So which means we're going to use the concept of m1 times m2 in order to get the gradient of the normal. So the gradient of the normal, actually, if you can open your eyes widely, you are going to see this is going to be -1, and this is the concept that we have used. So when t is 0, we can now get the value of x by substituting t equals to 0 into the original parametric equation, so that we can get the coordinates. So which will mean that we shall substitute it at this point and have our value as 1, and also in the second equation we shall substitute to get y, and we shall also get our final answer as 1 as well. So we have the point where this normal is going to pass, actually is on the point 1 1, and then we can use the equation of a straight line, which is y equals to mx plus c, and substituting the coordinate points and the gradient that we had obtained, we can be able to find the y-intercept c. So the y-intercept here is going to be 2, which will mean that now our equation can be written in the form y equals to mx plus c, or it can also be expressed as y plus x plus y equals to 2. And if you are finding value in this video, if you are finding value in the way we are working out these questions, and you are learning something, I would like you to take a moment and subscribe, and also you can leave a comment down below if you really understood the concept on how to work it out. All right, so I want us to change the gear and have a look into the examination question, the way a question has ever been asked in the past exams, because it's very important. It's important for you as a candidate to ensure that as much as you are revising and you are doing these questions, to look at the past paper question to see how are questions asked in a given area, so that you get to prepare well. So let us look into the examinations and get to pick a few questions which have been set before. Now let's delve into it and get to see what question might have been tested before. So what this one of the question, and you are given the parametric equations to a curve being x equals to 2t minus tan t, and we have the y equals to ln of sine of 2t. So you are supposed to show that dy dx is equals to cot t. How can you go about that? So first we have to differentiate y and then differentiate x, so that we can combine to get the y dx. Remember, when you are differentiating ln functions, it will be the differential of the function f of x over f of x. So meaning, in this dy dx, we are having the function is 2 sine 2 theta, rather that is sine 2t. So first we are going to differentiate sine 2t. So we are having two functions again there. So we have sine and also we have 2t. So we shall start by differentiating the sine function, and differential of a sine function is cosine. So we shall have this as cosine 2t. Next, you differentiate times the differential of 2t, and this is going to be what? T, just 2. So meaning that we shall also write now the function f of x there, and that's going to be sine 2d at that particular point. Moving further down, we can simplify this to 2 cos 2t over sine 2t. The next part we're going to work on is differentiating dx dt, and basically this is differentiating 2t, we are going to get just 2, minus differentiating tan t, we are going to get sec squared t. If you want to be safe on doing these particular questions in exams, make sure you understand fully, you have a good and a perfect understanding on how to do differentiations, so it becomes very easy in order to work out these particular questions. So moving on, now we're going to delve into finding dy dx, but we have to simplify sec squared t. Remember, from Pythagoras theorem, sec squared t is the same as 1 plus tan squared t. So we can be able to write that and then simplify that further. Of course, we're going to open those brackets later and see what we are expected. So let us open the bracket here. We shall have 1 minus tan squared t, and this particular part can also be simplified to 2 over tan 2t, because you see we are having cos 2t over sine 2t. So that is now the inverse of a tan function. Now, from trigonometry, there's something very important also we need to look at. We had said that tan 2t, 2a equals to 2 tan a over 1 minus tan squared a. But if you look at that, we can be able to make 1 minus tan squared a the subject, and then we can be able to express it in that form. So that we're going to write this in form of the new dimension that we have expressed on the other part. So instead of having dx dt equal to 1 minus t squared t, tan squared t, we shall replace that with 2 tan A over tan 2A. So when we are writing this, but that can be A can be expressed in terms of t, because in our parametric equation we are having t, we are going to have this simplifying to what? Let us write now, that is 2 tan t over tan 2t, that is our dx dt. Then now let us go ahead and write dy dx can be dy over dt over dx over dt. And then we can now substitute our dy dt into this part, which is going to be what? Divide by this part. Then we can now interchange the fraction, and then we start cancelling out, because remember, when you are dividing the fraction, you to change it to a multiplication, you are going to interchange the denominator and numerator. Then at this particular point, this part and this part will commit suicide, and then we shall also cancel these two guys out, and we are going to remain with our final expression as dy dx equals to 1 over tan t, which is the same as cot t. And actually now we have proven that dy dx of those parametric equations is equivalent to cot t. I wish you all the best in your revision, and basically, as you continue revising, make sure you subscribe before you leave this channel. See you in the next video.